right, let's go. Let's begin. 13D. Now, before we get to 13D, we have to revise what you learnt in 13A, 13B, 13C. Then you can see that how 13D kind of finishes off with what you need to know for exponentials, yeah? So let's go back. What was 13A about again? Someone remind me, what was 13A about? Let's go, Will. Name me one thing from 13A. What did we learn? What did we learn? It is a very good question because it links to what we're doing today. You completely forgot. Yasmin, what did we do? 13A. What's the very first thing I taught you? Index laws. So we learnt index. Oh, really? Index laws. Because that's the same with Meredith. That's where she's ran off to. So, index laws. There were 7 laws in total. Give me one of the laws that you've learnt, Hamish.
Plus in the powers.
Plus in the powers. When do you plus the powers, though?
When it's like division this and this times this.
Very good. This and this times with this and this, right? So it'll be like a to the power of m times a to the power of n. You can add the powers only when you're multiplying them. But what do you have to make sure on that rule in order for you to add the powers? Something has to be true first. What has to be true? So if I gave you 3 to the power of 4 times 3 to the power of 7, yes, you can add the powers. But why can't I do it if I had that? What's the problem? What must occur in order for you to add the powers? Why can't I just do 4 plus 3 right now? Yeah, 3 and 7, they have different bases. Okay, so the bases have to be the same. That's what the rule's saying. Both letters are the same. Okay, so that's rule number 1. If you multiply the bases the same, you can add the powers. Then what's rule number 2 then? Can I please have, let's go Seb.
If you have in brackets like a, then m in brackets.
Yep.
Then you have n outside.
Good.
Times the powers.
Very good. It's a to the power of m times n. Give me another rule that you learnt. Let's go with Rachel. Give me another rule. Another index law rule. What's the opposite of timesing? If you have a to the power of m times a to the power of n, you add the powers, you minus them. So if you have a to the power of m divided by a to the power of n, you subtract the powers. So we've got add the powers, we've got times the powers, we've got subtract the powers. What else do we also have, Ben?
M divided by n is the nth root of a to the power of n.
Very good. So the nth root of a to the power of m is equivalent to a to the power of m over n. The nth root, so if it's third root or cube root, fourth root, it goes to the denominator. So that's very important. As a rule, most students will forget this rule. This is like, let's say, a to the power of 1/8 is the same thing as saying 8th root of a. Okay, so that's just one of the things to pay attention to is currently a to the power of 1, 8 as the root, nth root. Okay, what else did we learn? We've got 1, 2, 3, 4 there. I'm missing another 3. What's the other 3? Give me another one. Anna. I'll give you a hint. Something to do with the 0. Good. A to the power of 0 is equal to 1. Anything to the power of 0 is equal to 1. Give me another one. If it's not 0, you can also have what else? Steph. Negative. So if you have a to the power of negative m, this is the same thing as writing. Good. 1 over a to the power of m. Okay? Now these are the 2 rules that most students forget, which let me show you. It's this one and this one. Like I said, anything to do with fractions, negatives, or surds, most students don't do well. The others, most of you will remember. Okay, most of you will remember adding, multiplying, subtracting, and to the power of 0. Most of you remember that. Now I've got 1, 2, 3, 4, 5, 6. What is my last one? What's the last rule?
Is that the one where you do like a, m in brackets, the m equals a, m, but a to the m?
Very good. So for those of you who may have forgotten, the last one, it's really an extension of this rule. It's an extension of a to the power of m all to the power of n. So the 7th rule would be something like a to the power of m, b to the power of n. If you do it all to the power of, let's say, c, this is the same thing as writing a to the power of m times c and b to the power of n times c. So it's very similar to this one where you multiply n to the m, you multiply c to the m, c to the n. Okay? That's the same with division as well. If you had a to the power of m divided by b to the power of n, and if they're all to the power of c, it's the same thing. It's still a to the power of m times c over b to the power of n times c. Okay, that's your 7th rule. These 3 are the common ones that most students will encounter. Those are the kind of problems that will come up in your SACs, your set of questions. Those are the ones you're going to be using to solve. These are the basic skills which most students will be able to do. So most of the time when I'm marking the SACs, I know that most students will tick off these boxes. It's these ones I want to focus on. Okay? Because that one is really just an extension of this, but for whatever reason, having more numbers and letters inside a bracket makes it scary for a lot of students. Okay, so I want you to write that, this one, that one. That's exercise 13A that you can take out. Okay? 13B was pretty much putting in the negatives of these two. So 13A, basics. 13B. Okay? So 13A, 13B goes in together. It's all index laws right now. Then we added on an extra part of 13B. The reason why you need to know surds was to allow you to break something like 125 to the power of 2/5. Okay? What was the skill that you had to learn in 13B in order to break or solve this issue? Instead of using a calculator, what was the one skill you had to learn for 13B on top of knowing the rules? There's a name for it, starting with F. What was it called again? Anyone have a clue? We do. Starting with F. How do I solve 125 to the power of 2/5? Someone said something? No? Factor tree, okay? What is a factor tree though? So I gave you a name, factor tree. Well, what's a factor tree? What's a factor tree? What am I doing with factor tree? How do I use a factor tree in this case? What's a factor tree? Someone describe that to me. What's a factor tree again? Fantastic. So, if you break down its factors, that's why it's called a factor tree. Now you can think of any number you want. You just need to break it down to smaller chunks. Now 125, you can either jump right to the actual problem, or I know that it's multiples of 25, and I know that if I did 25 times 5, that will give me 125. Okay, because you got 4 25s in 100 with an extra 25, that makes 5 groups of 25. Yeah? So what I've just done there is I've broken up 125 into 2 factors. 25 times 5. Now 5 is a prime, so I don't need to break that any further. I want to break it until I get to its smallest factors. Now 25, you can break that further into 5 times 5. Now the cool thing about this is you can rewrite 125 as 5 times 5 times 5. Because you broke it into its factors. Because 5 times 5 is 25, and then 25 times 5 will give you 125. So 5 times 5 times 5 is the same as 125. Now why did I do that? Because now you can say 5 times 5 times 5 to the power of 2/5. You can rewrite that as 5 to the power of 2/5, or you can write it as, 5 cubed to the power of 2/5, which is the same thing as writing 5 to the power of 3 times 2/5 using the rules that I've just shown you. And now you can say it is 5 to the power of 6/5. Okay? That's simplifying it. Obviously, the questions you get in 13B will allow you to evaluate it. All I've done is simplify. But what have I done? The one skill that you're adding on is a factor tree. And then what am I doing here? I've collected 5 times 5 times 5. Law number 1. And then law number 3, when you multiply in brackets. When they're in brackets, you multiply them. So I did 3 times 2/5. And it simplifies to 6/5. Okay, so you can see I'm using 13A, add it on with a factor tree to do 13B. Okay. Now, hopefully by now you would have done 13A, 13B. I'll be checking your homework this Friday. Okay. Look, it's been like, this is our 4th week, and you're very lucky I haven't even had a chance to catch up on you guys about it. So, this Friday I'm checking your homework for 13. Okay? But, here we go. 13C. Almost there. 13C. 13C. What did we do in 13C? That was our last session. It was on our last week. Good. Transformations of exponentials?
To the bx plus c plus d.
Good. Let's do some examples to recap your memory.
Which exercise would you want to
I'll be doing ABC because that ABC will tell you the basics, and if you can do D, then I already know that ABC is done. Yeah, but ABC has to definitely be done, otherwise you're falling behind too badly. Because by the time I get to logarithms, the inverse of exponentials, if you're not done with exponentials, it's going to be really hard to catch up with logs. Okay, this is all revision of what you've done year 9 and 10. Okay, and if I teach logs, you have to know your exponentials. Okay, here we go. 13C, let's start off with an example. Let's say I gave you y equals to 2 to the power of x plus 1. So let's start off easy. What's the plus 1 do to the graph again? Can I please have, yes, Seb?
That shifts it up by 1.
Good, shifts it up 1. Okay, so my graph, remember I told you there were 3 properties and I wanted you to copy down the 3rd property. But let's go 2 to the power of x. I know normally it looks like this. That's my exponential graph. But they had properties here. There were 2 properties. What were the 2 things that you definitely knew about exponentials? Name me one of them from 13C. What was the first property, Ben?
Y equals 0 is the asymptote.
Good. We have an asymptote of y equals 0. So 2 to the power of x has an asymptote at y equals 0 because we know you're always halving in the negative direction. It gets smaller and smaller and smaller, but never gets 0. So we call it an asymptote. What else? There was an asymptote. There was another thing as well. What's the other point? What's 1?
Sorry.
What is 1?
The y.
The y-intercept. Because we know, using our rule from here, we said that anything to the power of 0, it has to equal to 1. And we know that if I let 2 to the power of x become 2 to the power of 0, the y values is always 1. So when x equals 0, y equals 1. That's why you have a y-intercept at 1. Okay? But now, if I said I shift everything up by 1, how does that change things though? If I had an asymptote at 0 and I had a y-intercept at 1, which looks like this, if I shift everything right now up by 1, what would change? What would change? Charlotte? What would change? If that's my graph for y equals 2 to the power of x, that's my properties, y equals 0, 0, 1. If I shift the graph up by 1, what will change? The y-axis intercept, and what else would change? If I moved everything up by 1, what else would change? Asymptote. Logically, the asymptote now would move from 0 to 1 because you moved it up by 1. So the asymptote now will be at 1. So the graph should look something like this. I'm going to do it in green. So it should have an asymptote now at 1, so y equals 1, and it still moves like that. The only difference is, instead of at 0, 1, it would now be at 0, 2. Because you went up by 1. So the y values would have gone up by 1, 0, 2, and that's my graph. Okay? So we know that the 1 will tell you up or down. What else do we know? I'll give you another one. Y equals 2 to the power of negative x. What does the negative x do to the graph? What does it do, Yasmin? With the negative to the x, what does that do? Not sure? Next one, Anna. Say it again. That is true. This is 1 over 2 to the power of x, but it still doesn't help me to visualize. Oh, it could. It could, but I want to know what does the negative to the x do again. So going back to chapter 7 transformations. What does the negative to the x do again? It is a reflection in which axis? Is it the x-axis or the y-axis? Y, because you're affecting the x values. Yeah, so think about it. If you're affecting the x values, it now becomes negative 1, 1. So if you change the x values to become negative, it flips in the y-axis. So what does your shape look like now? This is what it'll look like. 2 to the power of negative x will be like that. Let's go with another one. Y equals negative. What if I put a negative outside? What would that be now? If a negative is on the 2 to the power of x, so it's negative on the outside of 2 to the power of x. Yeah, because if this was the positive values, putting a negative on it just means all of these dots here become negative. So it flips down. Reflection in the x-axis. Okay, so you got reflection x-axis, reflection in y-axis. Now, what if I gave you y equals 2 to the power of x minus 1? What does this do to the graph? Makes it go to the right. Same way that you would have done for quadratics, cubics, or anything you learnt in chapter 5. It's what you're dealing with the x's. And I gave you guys a tip. I showed you how to solve for this. I said, let x minus 1 equal to 0. Solve for x. If x equals 1, it means to the right by 1. It's still the same techniques. Okay? And hopefully from last chapter, you learned from chapter 7 that the reason why I let it equal to 0 is just to make it your life easier. It's actually meant to be equal to x, and that's meant to be x dash. So when you rewrite it, it just tells you it's x dash equals to x plus 1. That means your original x, you add 1 to move to the right. But I didn't teach you that to start off with. I said let it equal to 0 and solve. That was the reasoning for it. Okay? So that moves to the right by 1. 13C, your job was to only read the transformation so you can picture what the graph looks like. 13A, 13B, you've learned the algebraic skills to solve. Now 13D, you're putting all that together because you're going to learn to solve equations that are exponential. Okay, so if you can solve equations that are exponential, that allows you now to find intersection. It allows you to find when does the graph touch the x-axis or the y-axis, because you can let it equal something and you get an equation you can solve. So without 13A, B, C, you won't be able to do D and E. So you can't sketch, you can't solve, therefore you can't analyze. Okay, so it's very important that by this Friday I expect 13A, B, C to be something that you should know. Yeah, because you're going to do the same for logs. Logs, you're going to learn the rules, you're going to learn the algebra to it, you're going to learn the transformation for it, and then you're going to sketch. It's all the same. Everything you learn from methods are going to follow that sort of template. It's going to be algebra, solve, sketch, and then analyze. It's always in that sort of order. Okay, so that's why you have to learn the algebra. If you don't know the algebra, you can't move forward. There's no point in me telling the theory, because it just wouldn't help you. Okay? All right, here we go. Let's do some solving problems. Here we go. First one. 4 to the power of x equals 256. Now, unlike how we're used to using algebra, we normally do the inverse to solve. You haven't learnt the inverse of exponentials yet. So the only way to solve at this point is what we call by solving, by equating to solve. Okay? We call it by, I forgot the name for it. I think it was, no, I forgot the name for it. Okay? We're just basically saying that if the left-hand side equals the right-hand side, then therefore these two must be the same. So I'll give you an example. If I said this is 3x equals to a times x, naturally you would know that a has to be a 3. Only because this was 3 times the x, then on this side something times x has to be the same as 3x. So we're using the same logic. We're saying, all right, well then if I have 4 to the power of x, if I can somehow change 256 with a 4 to the power of something, then I'll be able to figure out what x is. Okay? Now, most of us won't know 4 to the power of what will give you 246. So what you're going to use is a factor tree. Yeah, it is 4. But you're going to use a factor tree to help you, 13b, to break this down. So let's break this down. 256. We're going to rewrite it again. 2, 5, 6. Let's break it down. Give me 2 numbers that you think that multiply will give you 256. Any numbers would work. Yeah, you can halve it if you want. You can halve it. It makes it easier if you halve it. So we halve it. Divided by 2. How many 2 goes in 256? 128. Okay, we can break that even further. 128. If you still don't know what 2 numbers, halve it again. Because they're even numbers. It's easy to halve. So if I halve it again, what's half of 128? 64. Now it's going to make it easier. 64, you can get numbers that multiply to give you 64. You can do 8 and 8. Yeah, yes you could. You could do 32 and 32. I mean 32 and 2. Okay? But you can break it down now. It becomes 4, 2, 4 and 2. And this is nice because remember I said I wanted a base of 4. That's what I want. I don't want the 2s. 2's not a problem. But the nice thing is I can probably collect them all together. So you think about 256 is equivalent to 4 times 2, 4 times 2, times 4 times 2, times 2 times 2. That's the reason why you do a factor tree. Okay, a factor tree, you can break it down and you can say this is the same as 4 times 2 times 4 times 2 times 2 times 2. All I'm doing is I'm just multiplying by their factors. Because that's what we're saying. We said that 128 is made up of 64 times 2, but 64 is made up of 8 times 8, and then 8 is made up of 4 times 2. So if you break all that down, it's easier to say now you can collect all of this, and you can simplify that line down to this. See, that's a 4. This is another 4. But you got 2 times 2 gives you another 4, and then 2 times 2 gives you another 4. And that's what Seb said. 256 is 4 to the power of 4. Just in case you didn't know. So if you didn't know, there's always a skill that allows you to break it down so that you can figure it out. 4 times 4 times 4 times 4 is 4 to the power of 4. So now you can say now, 256 is the same thing as writing 4 to the power of 4. Now if both left-hand side and right-hand side are equivalent, then x has to be 4. Logically. Because we're just saying left equals right. And if they're both equal, both sides have to have the same amount in every way. And it just so happens that we've got them exactly looking like each other, therefore x has to be 4. Okay, that's all you have to say. So right now, we are just solving by equating. When you get to logarithms, you won't have to do this method anymore. You've got a CAS, and you can use a calculator to solve, but this is one of the ways to do it without a CAS. Okay, you break it down. So the better your factors are, so 13a, 13b allows you to simplify the problem, so you can do that. Okay? Yes?
During the assessments, do we have to do it if fast? We have to do it that way?
It's likely that in the assessments that you get, it will be an exam 1. And if it's exam 1, you'll get questions like this, then you have to do it by hand because there's no CAS. And you can't leave your answer as log base 4 of 256. That wouldn't be considered simplified because you're meant to know what the answer is. Okay, here we go. Let's go to the next one. Same thing with 3 to the power of x minus 1. Now, if you have a look at this problem on the left, it's the same thing. We can only solve if it has the same bases. So right now I've got 3 to the power of x minus 1. My goal is to make 81 to the base of 3. Okay, now if you don't know what 3 to the power of what will give you 81, break it down. Now let's break it down. 81, how can I break this down? What two numbers that multiply give you 81? 9 and 9. But the nice thing is 9 and 9 can be broken up to 3 and 3, and you get another 3 and 3. So really, if you wrote 81, it's really like 3 times 3 times 3 times 3, which another way of writing it is 3 to the power of 4. Okay? So once I did my factor tree, I can say, oh, 81 is the same thing as writing 3 to the power of 4. But here's the thing. If left-hand side equals right-hand side, and they're both the base of 3, then that means the powers have to be the same as well. So x minus 1 has to be the same as 4. That's what you're trying to say. You're saying that x minus 1, which I'll write over here, x minus 1 has to equal to 4. These two have to be the same because apparently the equation's equivalent. So if it's equivalent, the powers have to be the same. So now you can solve it. X minus 1 equals 4. Therefore, x has to equal to 5. Okay? So that's what 13D is. 13D is using your skills from what you learned in 13A, 13B, so you can solve. Let's do the last one. Last one, same drill. Same drill. This one is 5 to the power of 2x minus 4 is equivalent to, now the problem is, you got 25 to the power of negative x plus 2. Problem is, this is a base 5. That's base 25. I need to make the bases the same first before I can compare them. The nice thing is 25 is easy to break down. How do I break 25 down into base 5? What do I do? How do you break 25? What does it become? Yeah. Yeah. It's just 5 and 5. So 5 times 5 is the same thing as saying 5 squared. So I can write this now as 5 squared to the power of negative x plus 2. And on the left-hand side, I still have 5 to the power of 2x minus 4. Now, this is what I mean. 13a, 13b. What rule can I use right here? When you have the brackets, you got a power on the outside. What was the rule again? What do you do? What can you do to the powers?
You times the base.
Yeah, you times them. That was the rule that we wrote over here. That rule right there. You said a to the power something, but you can put it all in brackets to the power something, you times the powers. So in my case, I would now follow this rule and say, all right, let's solve it. This would now be the same thing as writing 5 to the power of 2. Now be careful here. When you say times, remember this has a negative x plus 2. There's 2 terms there. So when you write it out, that's how I would do it. Okay, I would write the brackets so that you could see it's multiplying the 2 terms. And over here, this is 5 to the power of 2x minus 4. Most students at this stage, if they don't do the brackets, they make a mistake and they say it's 2 times negative x, and they forget to times the 2 with 2. Okay? By putting it in brackets, it reminds you that not only are you doing 2 groups of negative x, but you're also doing 2 groups of 2. Okay, so now if I do that and expand the brackets, you will get 5 to the power of 2x minus 4 is equal to 2 to the power of negative 2x plus 4. Whoops. 5. Thank you. Okay. Now you can say, by equating them, left-hand side equals right-hand side. If bases are the same, that means powers are the same. If powers are the same, then you can say, therefore, 2x minus 4 is equal to negative 2x plus 4. Now you can solve it. Add 2x on both sides. 4x equals to 8. X equals to 2. Okay, so I'll just zoom out a bit so you can see the steps. So what are the key steps here? That was 13a, but like I said, there are 3 things that most students find difficult. It's when you have the brackets. So that's rule number 3. You can have the ones with the negative powers. You can have the ones with the surds. Those are the common ones that most students find difficult to solve. Okay? Right here, be careful with the times. When you times the powers, make sure that you times every term. I use the brackets to help me. Okay? Solving here is just linear equations, adding 2x on both sides, adding 4 on both sides, I get 4x equals 8, x equals 2. Okay? How are we feeling so far? Does that make sense so far? That's 13D. You're just solving for equations. Yeah? Now, I'm going to show you one that it comes up in the year 12 exam, and I always show it to my students every year in year 11 because whatever you learn in year 11 is accessible for year 12 next year. Everything I teach you now that you're learning is usable for next year's exams. That's why the hardest years to learn is actually year 11, not year 12. The time that you learn the most is in year 11, not year 12. Yeah, year 12 is to refine your skills. Year 11, you learn the techniques. So learn it all in year 11, and you get a bit of a easier time in year 12 because you get less time in year 12. So here we go. I'll show you this problem here. Remember last session? I think it was last session. Yep, it was last session. I mentioned to you that the skill I wanted you to take out of 13B question 3 was to learn the skill of making the problem easier for yourself. And I told you guys to try to find a repetition. Find a repetition, find something that you can replace to make your life easier. This is a classic example that my year 12s will always get. Okay, it comes up every year for question 3 exam 1. No calculators, and you have to solve this by hand. It's very easy if you can change it to a quadratic problem. It's always a quadratic problem. So, let's have a look at this one. I'll do the first one and see if you can do this one. Okay, it's the same skill. Your aim is to replace something to make it easier. Now, because I've done it so many times, when I see these kind of problems, I know straight away that I have to replace it or make it a quadratic. But I'll show you what I see. You see, when I see that 3, I see it's 3 to the power of x. I see that this is 9 to the power of x. And immediately I'm like, well, that's a problem. If I were to do this without a calculator, I can't do it by hand. But there have to have been something about these two that make it similar. And what I can see is 3 and a 9. 9 can be written as 3 squared. This is 3 to the power of x. But this is 3 squared, which is 9 to the power of x. Now, another way of looking at 3 squared to the power of x is, that's the key step. Why are these two the same? Can someone explain to me what I just did there? I did 3 to the power of 2, all to the power of x. Why is that the same as 3 to the power of x all to the power of 2? Someone explain to me.
Well, the whole stage of either multiplying one side bracket without that bracket, and either way, you would the answer will still be the same.
Exactly. Remember the rule? This rule over here, I'll just go back. It's always going back to this third rule. This third rule right here. We said, if you have a bracket to the power, it'll be m times n. But the thing is, m times n, doesn't matter if it's n times m, so a times b or b times a is going to be the same thing. So what I did over here was I used that skill to recognize that 9 to the power of x is the same thing as writing 3 to the power of x squared. Because at the moment 3 squared is 9, that's true, but 2 times x is the same thing as saying x times 2. Now why did I write it in this way? Because you can now see this has 3 to the power of x. This is also 3 to the power of x. And like I said, if you see a repetition, okay, it's going to happen throughout the years. If you find an exponential log problem that's hard, it's likely to be this kind of problem. It's always going to come up. Okay, I promise you when we get to logs, it's going to have a similar problem to this as well. If you can find something that you can repeat, do what I'm trying to teach you here. Use something like this. If I said, let a equal to 3 to the power of x, suddenly your problem gets easier. Why is that? Instead of 9 to the power of x, I now have a to the power of 2, because I'm replacing 3 to the x. That's equal to 12 times. Now instead of 3 to the x, I said, let it equal to a. This is minus 27. See, this equation right here comparatively looks much easier than something like that. And all I've done is I've just changed it by saying let a equal to 3 to the power of x. Okay? And how did I know it's 3 to the power of x? Because I noticed 9 and the 3, they have a relationship of 3. So 3 squared is 9. Instead of writing 3 squared, I can write it as 3 to the x. 3 dx, 3 dx. This changes this problem here. Now, if I want to simplify that problem even further, you can write this as now, a squared equals to 12a minus 27. If I rearrange the equation, you can get now a squared minus 12a plus 27, and on the right-hand side equals 0. See that? If I gave this to you initially, if I said solve this, most of you had an idea. Most of you will have an approach. But if I go back to the very first line, most students go, oh, I don't know how to do it. Right? This is what I'm trying to say. Using that letter to try to make your problem easier by recognizing any repetitions, that's the skill that you want to take. Okay, so here we go. A squared minus 12a plus 27. Let's factorize. Because they're all equal to 0 on the right-hand side. What does it come down to?
Negative 3, negative 9.
A minus 3, negative 5. Does that work? Let's go.
9.
9?
Yeah.
Okay, that's true. There we go. Negative 3, negative 9. And yes, that is true. So therefore, using null factor law, a has to equal to 3 and 9. Okay, but we're not done yet. Because a was something I made up. I made up a. A never existed. I made it up just to make it easier. So you have to think back. If a equals to 3 to the power of x, you have either a equals 3, which means it's 3 to the power of x equals 3. Therefore, using what you've learnt this exercise, if both bases are the same, powers are the same. So x has to equal to 1. Okay, so that's my first solution. I have therefore x equals to 1, because this is 3 to the power of 1. Next one. 3 to the power of x can also equal to 9. Change the bases so they're the same. 3 squared, so therefore x equals 2. See what I'm doing there? This is a very typical example. 3 marks for next year out of 40 marks. 3 out of 40 is a lot of marks for something that you can do now.
Is that year 12?
That's a tip. I'll find one right now. Actually, I think I actually even have on my PowerPoint that I've uploaded years ago. But let me show you how often or how common they come up. Where is the exponential? Whoops. Where's 13? Was it D? Where's my D? Do you see D? Oh, there we go. That's my probability. Did I put an exam question in there? Is that an exam question? No, those are your textbook questions. While you guys are doing your work, I'll find the exam question. I'll show you how easy it is. 3 marks. The reason why it's 3 marks for year 12 is because you get an approach, you get an answer, but usually one of the answers is impossible to do. Okay, so it'll be something like 3 to the power of x equals -1. And you can't have an exponential graph with a negative value. Then you have to say x can't be negative. That's how you get your third mark.
Do you write undefined?
Yeah, you say undefined, or you say therefore x can only be that because x is undefined, or x equals 2 is undefined. That's where you get your third mark. It's always a nice 3-mark question, or something like this is very easy.
There you go. Only 30 seconds to go.
But there you go. I'll leave that there. That's all you need to know. So that's 13D. But remember, this Friday, I'm looking for ABC as your basic skills so that we can move forward. Without ABC, you can't do D. If you can't do D, you can't do E. You can't sketch. If you can't sketch, then there's no point in me going to logs. Right? But I have to go to logs anyway. I'm just saying. Keep up. ABC is very important to do. Okay? All right, I'll pause the video there, and I'm going to find that exam question so you guys can see.